Thank you very much, and thank you to the organisers for the invitation to this very interesting meeting. So I'm coming rather from the physics side of the people here, and what I want to do today is to talk about some recent work on a couple of different types of models which show dynamical phase transitions in their current fluctuations, and try to explain how that can be understood within the framework of large deviation theory. So let me give you an outline so you know where we're going. I'll start with quite a brief introduction to the idea of current fluctuations, which is of great interest in non-equilibrium statistical physics, as we heard last week in the series of talks by Bernardo. And then, of course, large deviations themselves need very little introduction to this audience. And then in the main part of the talk, I'll talk about some pieces of recent work, in particular some joint work with Hugo Touchette on current fluctuations in a particular type of reset processes, and how they can be connected to a very old equilibrium model of DNA denaturation. So that's DNA, and I'll explain the connection later on. And then if there's time at the end, I'll more briefly talk about some other work, which was chiefly done by Massimo Cavallaro, who was a PhD student with me and is now a postdoc in Warwick, talking about hidden states in the zero range process and how the temporal correlations there change the current fluctuations. So both of these type of models show dynamical phase transitions, and I'll try to give some general perspective on that as we go. So I'm going to be interested in currents, and in particular in distributions of currents in stochastic particle systems with one particle or many interacting particles. And for concreteness, in the terminology we heard last week, I'm going to be looking at the microscopic picture. And of course, there are many different ways you can define currents, but let's consider one example. You might look at the current across a particular bond in particles moving on a lattice. So I choose some bond, and I count -1 every time a particle jumps backwards, and +1 every time a particle jumps forwards. And I do this for some time t to get an integrated current. And non-equilibrium systems, so with broken detail balance, not reversible, are characterized, as we know, by non-zero mean currents in the stationary state. But I'm going to be interested in more than means, in distributions, and in Markov processes, the distribution of the time average current. So I take this net number of jumps that I've measured and I divide by the time to get a time average. Distribution of the time average current generically obeys a large deviation principle, which I write very loosely in this way. So this rate function I of j tells me about the asymptotic probability of rare fluctuations, how likely I am in the long unit to see a fluctuation away from the mean or typical value. And of course, as we know, I could equally well look at the generating function. So I define here my generating function, capital G, and that will be important later on, as the average over stochastic histories of the exponential of some conjugate parameter times the current. And that scales in the long time limit with an exponent, which is this so-called scale cumulative generating function. And we already get some insight here into the structure of non-equilibrium statistical mechanics. Just as equilibrium statistical mechanics involves Legendre transforms, so does non-equilibrium stat mech, because we know that if lambda k is differentiable, then the rate function is its Legendre-Fenchel transform. Of course, if lambda k is not differentiable, then the Legendre-Fenchel transform only gives the convex hull. And in general, non-analytic points in this scale cumulative generating function correspond to dynamical phase transitions between regimes where fluctuations are typically realized by different mechanisms. And then you might ask, well, what type of models show dynamical phase transitions? And we've already had mention of several models last week, and I'm going to talk now about two different types of models. So the first is this idea of reset processes. And there's quite a lot of interest at the moment in stochastic processes with reset. So you take some stochastic process, and at random time intervals, that process is reset to a particular configuration or a particular distribution of configurations, or perhaps you do something simpler and you just reset some internal clock, like you see on this sign. And the kind of paradigm for this would be a search problem, so you've lost something, you wander around slightly aimlessly looking for it, and after a while you give up and you go back to where you started from, and you start again. But there are lots of other applications in foraging, in population dynamics, which are suddenly wiped out by some catastrophic event, in the clearing of buffers, attachment to molecular motors, and so on. And I put the names here of some of the people who've been involved in that, and some of them are in the audience. So what we did, building on some earlier work on large deviations for reset processes, in particular by these gentlemen, we thought about the large deviations of current fluctuations in particle systems with reset. So let's be a bit more concrete. I'm going to start with a Markov chain, capital X, evolving in discrete time. And the transition probabilities in this Markov chain might have some weak time dependence in a way that will become important later on. And I'm going to assume that even if the transition probabilities have some weak time dependence, the original process has a large deviation principle for the current. So I have a current generating function for my original process, which I'll call G0. So the 0 will always relate to the process before I put the reset in, which scales in the long time limit with some scale cumulative generating function in the exponent here, and a corresponding rate function. So I take this process, and now I add reset in the following way. At each time step, with probability R, a reset occurs. And in that case, no current is incremented, so the current stays at whatever value it was at, and the process is reset to some fixed state, or some clock is restarted. With probability 1 minus R, then, the process evolves, the current is incremented, and there's no reset. And the question then is, well, what is the generating function with reset? So this subscript R to indicate the reset here. In particular, if you have a finite length of time between resets, you might expect that perhaps the finite time corrections to this G0 play a role in this generating function. And you might imagine that for a particular value of current, there's some optimal frequency of resets which will realize that fluctuation. And then you can ask, well, does that frequency change smoothly as I change the value of the current I'm interested in? Or is there some phase transition to a regime where the most likely way to see a particular current is just not to reset at all? So is phase transition of this sort? And it turns out that we can answer that question very easily and say quite a lot more by making a mapping to a much older problem. So this is the Poland-Scheringer model of DNA. It's over 50 years old now. And the idea of DNA, remember, is that it has two strands, and they're kind of wound together, and you're interested in the conditions on which they can be pulled apart, denatured. And in the Poland-Scheringer model, what we do is the following. So we say, I have two strands which are made up of bound pairs, and each pair can either be bound, as indicated here, or it can be pulled apart, as indicated here. So I have segments made of bound base pairs and segments made of unbound base pairs. And it turns out you can map the generating function in this model to the partition function for the current. Sorry, the other way around, you can map the partition function in this model to the generating function that we're interested in for the current in our model. And the way it works is the following. The bound parts here I associate with reset events, so where the current is not incremented, and the unbound parts I associate with the parts where there's no reset and the process evolves and the current goes up and down. So here's another bound part, another unbound part. And in the Poland-Scheringer model, what you do is look at the partition function for this setup, and you want to see what happens as you change the temperature, and in particular whether there's a phase transition to a regime where the whole thing is unzipped, so like at the top here, it's completely pulled apart. And you want to characterize that phase transition.
So Rosemary, so in this setting you can still talk about arbitrary Markov chain when it is not being reset.
Yes, yeah.
This is just some kind of bookkeeping.
Exactly, yeah, it's just a neat way to do the bookkeeping. In a moment we'll see particular examples, but at the moment xi is completely arbitrary. So in the PS model, the order parameter you're interested in is the fraction of bound monomers. In our model, we want to do something very similar, but we're looking for a phase transition as a function of the conjugate parameter k in the generating function. And we want to know whether there's a phase transition to a case where we have no reset, so where we only have these unbound parts. And the order parameter there will, of course, be the fraction of steps with reset. So once you've made that mapping, in fact, you can take an awful lot through from what's originally been done for the PS model. So let's start on doing that. So what we do first is we write down the generating function for a loop of n consecutive steps without reset. And that's very easy. It's the generating function for the original process, G0, multiplied by the probability that I have n steps without reset. And even easier, I can write down the generating function for n steps with reset, in which no current flows, so I just have r to the n for the probability of there being n consecutive steps with reset. And just as in the PS model, it's convenient then to do a discrete Laplace transform, a Z transform. So here I have the discrete Laplace transform of the total generating function, the object I'm interested in, the generating function for the loops without reset, and for the loops with reset. And this one's so easy you can write it down explicitly already. And this is like a grand canonical picture where the total number of steps fluctuates, so at the end you would have to tune your Z to match the mean length of the trajectory you're interested in. And because you've then removed the constraint on having the number of steps adding up to a fixed trajectory length, it's then very easy to work out generating function looks like, because it's made up of all possible alternating sequences of the u's and v's. So you simply have to sum over these sequences of u's and v's, and when you do that you get a geometric sum, which gives you the 1 minus uv part on the bottom, and then you get some boundary terms which give you the part on the top. So then in this Z transform picture, you get an expression or the generating function for the system with reset. And the scale cumulative generating function which we're interested in is then determined by the largest real value of Z at which this thing diverges. So here we are again. Here's the expression for the generating function, and we want to look at values of Z for which this diverges. And if there's no phase transition, it's very easy. The divergence is just given when this denominator is 0. So the scale cumulative generating function is the log of some Z star, which is the largest real solution of u tilde v tilde equals 1, so the denominator being 0. But if this value Z star of k reaches the convergence point of u tilde, you get a phase transition. You can show that the convergence of v tilde doesn't play a role here. But it can happen that for a particular value of k, reaches the boundary of convergence of u tilde, and then you have a crossover to a scale cumulative generating function given by the log of the boundary convergence point here. And if you look at this, this is just the scale cumulative generating function of the original process without reset, plus the log of 1 minus r, which is the price you have to pay for not resetting at every single time step. So this is a phase transition between a regime where I have a finite frequency of resets and a regime where the optimal way to realize a particular current fluctuation is just to pay the price and not reset at all. You can do a bit more than that. You can characterize the phase transition. And the type of the phase transition is determined by the behavior of U tilde in the neighborhood of its boundary convergence point. In particular, as we anticipated at the beginning, it depends on subleading power law terms. So I'm going to write my generating function for the no reset loops in the scaling form of a part which has the long time behavior of the no reset process, 1 minus r to the n for the probability of not resetting, but then some short time corrections in this power law form. And if U has this form, then you can show very easily by taking over the PS argument that if this C of k is less than 1, there's no phase transition at all. And that includes the IID case where C is equally 0, and also you can show very easily it includes the case where your Markov process xi is time homogeneous. On the other hand, if C is bigger than 1 but smaller than or equal to 2, then it turns out that the derivative of the Laplace transform generating function diverges at the phase transition point, and that corresponds to a continuous dynamical phase transition. In other words, a dynamical phase transition where the average length of a segment without reset is infinite at the transition point. So as you approach the transition point, the average length of a segment without reset gets longer and longer and longer, and it diverges exactly at the phase transition. On the other hand, if C is bigger than 2, then although U tilde diverges, it converges at the phase transition point, and that corresponds to a first order dynamical phase transition with a cusp in the scale cumulant generating function, in other words, a discontinuity in the first derivative. And in that case, the average length of a segment without reset is finite at the transition point. So it gets bigger as you approach the transition point, but it's still finite at the transition point, and then it jumps to infinity beyond the transition point. And this is exactly the same classification as in this old model of DNA, except with the added subtlety that in our model, this C here depends on K. So in the PS model, C is a constant, because the probability for the binding has the temperature in, not the probability for the unbinding. So we have a K dependence here, which means that the nature and the type of the phase transition depend on the reset probability in general. So let's see how that works for a couple of examples. So the first example is a very easy example. Let's take a random walk in which at every time step the particle does a step drawn from a Gaussian distribution, always with mean 0, so it's symmetric, but with a variance which depends on the number of steps since the last reset. And I take this form here. Then you can show that the generating function for n steps without reset, this U thing, has this form. You can show that exactly very easily where these are harmonic numbers. And then you can find the long time scaling limits of that. And it has this form here. So we have exactly the scaling form we were interested in with a C of k that is b times k squared. So if b is positive, then we have the possibility of seeing a value c greater than 1 and seeing a phase transition. So b is positive means the variance increases with the number of steps since the reset. And then you can check that by solving numerically for this z star and zc. And that's what I show you in this picture here. So in the black line, I have the scale cumulant generating function that corresponds to paying the price, having no reset at all. And the blue lines, I have the solution for ZC, so this one, for different values of B.
about one thing, because the k was a Fourier variable, or?
It's the conjugate parameter in the generating function.
Yeah, but then if your c depends on k, what does that mean in real time?
So it means, first of all, you have to see if there is a phase transition. If there is a phase transition, it occurs at some value of k, and then you have to plug that into here to see whether that value exponent is greater or smaller than 1. And you can show that if it's smaller than 1, you never have this intersection. So maybe the example helps, and ask me again if it's not clear. So the blue line is the b equals 0 case. So that's the ordinary time homogeneous Markov case between resets. And what you find there is that star, the log of that, gives you a generating function which goes here, you can't quite see it, and then gets closer and closer to this case without reset, but never intersects it. On the other hand, if b is 0.5, that's the yellow case, you see that this expression for the scale cumulative generating function gets closer and closer to the line without reset, and then does intersect it. And if you plug in the value of k you find here, so kc from here, into bk squared, you find that it's between 1 and 2, which is consistent with this being a continuous phase transition where the derivative is the same on both sides. On the other hand, if b is much bigger, if b equals 5, you find that the expression for the scale cumulative generating function with a finite frequency of resets intersects the no reset case with a different derivative at the side, and that corresponds to c being bigger than 2 and being in this first order transition. And you can see that as well, of course, when you do the Legendre transform to look at the rate function. So this is the same picture, but for the rate function. Again, the blue case, everything is smooth. It's close to this black line, but it never meets it. So as I look for larger and larger currents, I get closer and closer to the scale cumulative generating function for the no reset case, but I never meet it, and the rate function here. On the other hand, for the yellow case, I get closer and closer, and then I have a transition to the rate function for the no reset case. So for currents bigger than this case, it's worth me paying the price and not resetting at all. So if I don't reset at all, then I'm going to see steps with a larger variance, which makes it more likely that I see a larger current, but I have to pay the price for not resetting, and that's where this phase transition comes from. On the other hand, for b equals 5, then when I do the Legendre transform, I get this straight line section here, which gives me the convex hull of the rate function. But in fact, you can argue here that this is the true rate function you would expect, because if I want to see some current fluctuation that's here, the most likely way I see that is to have some finite fraction of my trajectory where I have no resets and some finite fraction where I have resets at some given frequency. And then the interpolation of these gives me the straight line. So this is this Maxwell construction that we heard about already last week. And it relies on the fact that when you do have a reset, you wipe all the memory of the past. Okay, so that's one example. And let me more quickly talk about a slightly more interesting example. So still single particle random walk. But now I take a Gaussian with a constant variance and a mean, a bias that depends on the number of steps since the reset. And again, you can find the scaling form for these loops reset, and you find now that the exponent in the denominator is minus bk. So it can be positive or negative, depending on the sign of b and of k. So if b is positive, then I'm never going to see a phase transition for k positive, so for currents larger than the mean, because this will be negative. But I have the possibility of seeing a phase transition for k negative. And indeed, that's exactly what you see. So I plot here the same thing again, the scale cumulative generating function, the black line, the case where I pay the price and I have no reset, the blue line, the case where b equals 0, so I have a time homogeneous case, and it gets closer and closer to the no reset case as I look for larger and larger fluctuations, but it never meets it. And then in yellow, e equals 1, where as I look for large negative currents, I see that beyond a certain value of negative currents, the most likely way is to pay the price and have no reset. So I find here, if I plug that into my exponent, the value of k I have here, I find a value of c between 1 and 2. This is a continuous phase transition. On the other hand, for b equals 5, I find an intersection here with a different derivative on either side, corresponding to a value of c greater than 2, and a first order phase transition. Notice also that putting the reset in here breaks the symmetry. So the derivative of the scale cumulative function at 0 is positive, so now I have a non-zero mean current, even though the original model had a 0 mean current in the long time limit. And you can do a similar analysis for random walks in discrete space as well. And in that case, you can explicitly write down generating functions in terms of hypergeometric functions. So let me
linear pieces here as well, or not?
Yeah. So if you did the rate, if you transformed the rate function, you would have a linear piece corresponding to this green line. Yeah, it's very similar. So there are a few more things you can do for this setup. You can very easily extend the analysis to calculate the joint rate function for the integrated current and the number of resets. And then if you look at the value of the number of resets per time step, which minimizes the rate function for a given time average current, that corresponds to the expected fraction of resets that you see to realize that current. And if you do that, you can check, and you can find that the dynamical phase transition point, the expected fraction has this form. So if the derivative of u tilde diverges, as it does in the continuous phase transition, and the expected fraction goes to 0 at the phase transition point, so the time between resets goes to infinity. On the other hand, if u tilde derivative of that with respect to z is finite at the phase transition point, which is the first order case, then you get a finite expected fraction at the phase transition point. And then you could go on and do more things. You could look, for example, at the large deviation properties of the ratio, the efficiency ratio of current per reset, which is related to questions in stochastic thermodynamics about efficiency. And then you can do a similar analysis for other setups. So, for example, if you make the Markov process between reset time homogeneous, but look at the case of having non-constant reset probabilities. Then there are at least two different things you could do there. You could have reset probabilities which depend on the time since the last reset, so that's a kind of non-Markovian reset. And the subtlety there is you have to worry about the fact that the last segment without reset has different statistics, because it's a kind of unterminated loop, or it's a meander. So this is like what L.A. Barkai was talking about last week. On the other hand, you could also take reset probabilities at a constant, but every time you reset, you draw a new reset probability for the next segment. And that's somehow in the spirit of statistics. But in all these cases, if you look at the power law corrections in the generating functions for the no reset segments, the U part, and the reset segments, then by this PS argument, you should be able to predict whether or not you have a dynamical phase transition and the order if you do. So what I'm going to do in the last 10 minutes or so is I'm going to talk about another type of model where also you see dynamical phase transitions. And this is a model with hidden states, and hidden states in a paradigmatic interacting particle model, which is this so-called zero range process. So this is a model in discrete space and continuous time. In particular, we looked at current fluctuations in the L-site open boundary version of this, which was introduced in 2005. So what you do is you take a lattice with L sites, on every site of your lattice, you can either have 1 particle or 2 particles or 3 particles or 742 particles. There's no exclusion, there's no limit. So this is a model with infinite state space. And then the rule for the dynamics is very simple. The topmost particle on each pile can hop to the right or to the left, neighboring sites with a rate μn, which depends on the number of particles on the departure site. So there's no dependence on the site you're hopping to, only on the departure site. That's why it's called zero range. And you can make this thing asymmetric by letting the particles hop to the right with rate p times this μn, and to the left with rate q times μn, where mu is some function of the number of particles n. And then at the boundaries, we choose to put particles in at this end with rate alpha, and take them out at this end with rate beta times this function μn. And similarly, at this side, I take them out with rate gamma times μn, and at this side, I put them in with rate delta. So you can have driving both due to asymmetric boundaries and a bulk driving if p and q are different. And it turns out that if this function μn is bounded, in the sense that it doesn't grow indefinitely as n grows, then if you have strong boundary driving, you get a condensation phenomena, and the particles just pile up at one side or the other. So you don't have a stationary state, you just have this growing condensation. And also in that case, even if you choose your boundary rates so that there is a stationary state, if you look at the current fluctuations, you see a dynamical phase transition in the tails. But I'm not going to talk about that. I'm going to concentrate on the easier case, where μn goes to infinity as n goes to infinity. So the more particles there are on the site, the faster they want to get off the site. And in that case, in this ordinary Markovian setup, there are no dynamical phase transitions. And you can calculate the scale cumulant generating function as the principal eigenvalue of some tilted generator and do your Legendre transform and get the rate function. And it looks pretty ugly, but actually it's quite easy to understand where this comes from. So what we want to do now is to take this Markovian case with μn going to infinity as n goes to infinity and put in some hidden variables. And we put in hidden variables in the following way. We assume that every site has a kind of clock variable, which we don't see. And when the clock is 0, the particles are not allowed to hop. And when the clock is anything bigger than 0, the particles are allowed to move. This is an open boundary version of a model that was introduced by Hirschberg and al. In 2009. Now, the interesting part is the dynamics for this clock variable. The clock resets itself to 0 every time you have a particle coming into the site. It's a kind of reset process, but a reset process that's correlated with the particle dynamics. And then the clock switches on with some rate c, which doesn't depend on the particles. So this mechanism obviously favors the piling up of particles, the congestion of particles, because there are periods when the sites are off. And if you just look at the particle configuration, it looks non-Markovian, because you don't see this hidden dynamics going on down here. Nothing in the simple version I'm going to explain. You can do more complicated things where you have different rates depending on the value of tau. So you can make this μn, when they hop, depend on what tau is. But I'm going to assume it's constant as long as the clock is on. And in that case, the zero-range process, this on-off zero-range process, has a very complicated structure of current fluctuations. And you can do some analytical things by looking in extended state space where you include this hidden variable. But it's quite technical, and I'm not going to go into the details, but you find quite complicated phase structures, and you can also look at this case where it matters whether tau is 1 or 2 and so on. But in particular, when you do this, you find there's evidence for dynamical phase transitions, and in particular for a first order dynamical phase transition even for the case where mu_n is unbounded, when there are no phase transitions at all in the Markovian case. So to try and convince you of that, let me look at probably the most simple thing you can do. Let's look at the case where my model only has a single site, makes the analytics much easier, and it's totally asymmetric, so particles only move from left to right. And I set my departure rate, mu_n, to be equal to the number of particles on the site. So if I didn't have this hidden variable, this would just be non-interacting particles. And I'm going to look at the large deviations of the output current in this model. The input current is easy, it's Poissonian. I'm going to look at the output current. And this is what you see down here. This is the rate function. So the blue thing here is the rate function of the input current. It's just a Poissonian with rate alpha. And the rate function for the output current, the result of our analysis is it follows this rate function for large current fluctuations. But for small current fluctuations, you instead see this linear section corresponding to a first-order dynamical phase transition. And these dotted points are the results of Monte Carlo simulations for increasing time, which converge towards the theoretical prediction. And you can understand very easily where this first-order phase transition comes from. If I want to see a zero current in this model, the easiest way to do that is just to look at a fluctuation where the site is off all the time. And that has a rate function c. So that's this point here. And then for currents in this regime, the most likely way to realize them is to have some macroscopic proportion of the trajectory where the site is off, and some proportion where it's on, and a finite current flows. And then the combination of these two gives you the linear section. So there's a first-order phase transition that comes from this hidden variable we put in. Okay, so I'm almost out of time, so let me just try and conclude a little bit. So, as we know, current fluctuations have a very rich structure, and it's sensitive to the underlying dynamics, and hopefully the examples I've shown have helped to convince you of that. In particular, correlations in time can lead to dynamical phase transitions. So in particular, we saw in the first part how sub-exponential terms in the reset process, or in the process without reset, are amplified by reset and lead to these phase transitions. And this kind of argument would also work for other compound processes. Sub-exponential terms can be amplified. In the second part, I showed you how this interplay of the hidden variable and the possibility for the particles to pile up, the infinite state space, also leads to a dynamical phase transition. And in some sense here, there's not very much new, because what we're getting is insight into these non-equilibrium models from old equilibrium models, where the long time limit in our non-equilibrium model is analogous to the thermodynamic limit in equilibrium. And just as in equilibrium, the generally accepted folklore is that you need long-range correlations or two diverging dimensions to see a phase transition. Then you might expect something similar here, that you need long-range correlations in time or two diverging dimensions, where one of those is the time dimension, to see a phase transition. And that seems to fit with work from other models, for example, those with continuous state space. So large deviation theory provides a framework for establishing conditions for such dynamical phase transitions. There are lots of open questions, but I think I'll stop there and have some questions.
For the reset case, would you say then that you have long-range correlation, and that's the reason? Can you, with the mapping to equilibrium, do you really have long-range correlation that brings the phase transition?
I mean, you have this kind of weak, yeah, I think it's a good question. You have this weak long-range correlation if you have these power laws in the transition probabilities in the process X, and somehow these are then amplified by the reset. Though, of course, as soon as you have a reset, you forget everything. So it's a sort of funny hybrid setup, but somehow it seems to be related to the correlations there. In particular, because if you put a Markov process for X, then you see nothing.
I have this question about this first order transition, right? So in your model, you allow these successive resets, right?
Yeah.
Suppose I say that there's a rule where if the state is already in the reset state, then it's not allowed to reset. Will the first order transition still be there, or?
I think you would have to look at it, because then you would have a different form for the generating function for V. That would be very simple.
Because these successive resets doesn't allow the current to increase for a long time, right? I guess.
I would still expect you do, and that's related, of course, to what happens in continuous, where the notion of consecutive resets doesn't really hold.
But it survives in the continuous.
Yeah. I think you do, but I haven't checked it. But you should be able to do it by a similar construction.
So usually.
I mean, you still have the alternating U and V. It's just that the V's can only be of length 1. But I think still the power law corrections in the U would probably give you a phase transition.